This is part 4 of the Module 11 lecture. In this section, we're going to talk about the standard deviation of the errors. In the next one, we'll talk about the coefficient of determination. And this corresponds to section 13.2 in your textbook. Right. One important thing that we need to note is that this population regression model assumes that the random errors associated with each observation are independent. So if you observe a particular value, the random value of that observation is going to be independent of the random error of any other observation. Also, for any value of x, the average of the random errors is 0. For any value of x, the probability distribution of the errors is normal. And for any value of x, the distribution of the random errors have the same standard deviation, sigma epsilon. These assumptions shown graphically means for a particular value of x, the random errors, the deviations of the values from the mean, are going to be independent of each other. The average of those deviations from the mean is going to be 0. And the distribution of those deviations from the mean, in other words, the random errors, the distribution of the random errors is going to be normal. And they're going to have a standard deviation sigma epsilon that is the same for any distribution at any value of x. Right, so this graph is showing you in graphical terms the 4 assumptions. All right, and one more thing I should say. We identified that the parameters a and b determine this parameter mu y given x. And also for each value of y given these 2 parameters a and b, then we can find the epsilon values. And there is one more parameter that we need to estimate, and that's the standard deviation of the random errors. And this is going to be a very important quantity later on to construct confidence intervals and to test hypotheses about the coefficients in the model. So the standard deviation of the error sigma epsilon is unknown and is estimated by the standard deviation of the residuals. Because remember, the residuals, the E sub i's, are the estimates of the epsilons. So the standard error, or rather the standard deviation of the residuals, is defined as the square root of the sum squares of the errors divided by n minus 2, where this sum square of the errors is just the sum of the residuals, rather, which is y sub I minus y sub I hat squared. N is the number of data points, x, I, y sub I, and n minus 2 are the degrees of freedom associated with these sum squares of the errors. I'd like you to notice the similarity of this equation with the equation we saw in Module 3 to calculate the sample standard deviation. So you see the sum squares of the errors is just, in here is y minus y average squared divided by n minus 1. Here is y sub I minus y hat squared divided by n minus 2. And the reason is minus 2 is because this y hat is determined by the 2 estimates, a and b. So again, just I wanted to point out that this calculation is not necessarily that different from this calculation. All right, so if we wanted to calculate this standard deviation of the residuals using this equation, we will have to calculate the value using the regression equation for every value of x in the data set. So that will take some work. So a better alternative, given what we have calculated already to find the a and b estimates, is to use this equation of the standard deviation of the residuals. So here we use the sum squares of the y's, or the sum squares of y minus the estimate of the slope times the sum squared of the xy divided by n minus 2. And from the sums that we calculated to find this estimate b, well, we have the sum of that y squares, we have the sum of the y's, and we already used this sum of squares of x, y before. So we have all that information to calculate this, and there is no need to fit the model and calculate the predicted values for every value of x in the data set. So it's easier to use the sum of squares that we already have calculated and then use this equation instead of this equation right here. All right, so let's go back to the example that we've been working with and see how we calculate the standard deviation of the residuals. So again, this is the same table that we used before where we calculate these different sums. So once you have the sums calculated, which are right here, then you can use them to calculate the sum of squares of the y's or the sum of squares of the xy's. So again, we use the sums, we plug them into these equations, and we find these values. So once you have those values, then of course, you will have calculated the estimate of the slope using the sum of squares. And then with this estimate of the slope and the sum of squares of the y and the sum of the squares of the xy, and the number of observations -2, then plugging all those numbers into this equation, then you can find the standard deviation of the errors or residuals, and that's 0.504. And as I mentioned earlier, this quantity is going to be very useful when it's time to test hypotheses about the intercept and the slope, and for the construction of the prediction confidence intervals that we'll see in other sections. All right, so I will stop here. In the next section, we'll talk about the coefficient of determination.